Hello all and welcome to this video on chapter 17. This will be the first of 6 videos working through chapter 17, which looks at differential calculus. We will start with going through 17a, which looks at the basics of differentiation and the derivative, and we will go from there. This video in 17a is going to be maybe more of a history lesson than a maths lesson, but it will cover the maths and show you why this method of mathematics or topic or field of mathematics was invented and how it is used. So first off, infinitesimal calculus, okay, or differential calculus. Is it just a bunch of rules or something more? Most people learn and apply differential calculus, and we'll get to these rules or shortcuts in the next couple of exercises. But they get used to applying the rules and forget where does it come from and what is it. It's very, very powerful if you actually understand what it is, and if you have a deep understanding of where it comes from, then you can apply that knowledge when attempting harder problems or problems that seem a bit left field or where you need to think outside the box. If you can apply the basic principles, then you'll be able to find a different way to approach the problem. So infinitesimal calculus. What is it? Well, it's a field of mathematics, and you'll see there in red the word calculus is in bright red, and we'll see if my pen's working. Yes, it is. Okay, calculus. This word calculus, okay, comes from some other words. It's Latin, and there's a couple of words that are similar to it. I bet you know one of them. Okay, calculator. Okay, calculator. They both have the same sort of origin, and the word calculus, it comes from the Latin word for small pebble. Okay, now what the hell does small pebble, calculus and calculator have in common? Well, small pebble, someone decided to put them in a row and use them to add up things, and they made this thing called an abacus. Okay, and they used that abacus to perform calculations, or they used the small pebbles to do calculus. Now, calculus itself, before the 1600s, okay, before the 1600s, really meant maths. Okay, calculus meant to calculate, to do maths. Okay, now this field of infinitesimal calculus that was invented in the 1600s was so important. It was so important they effectively have called it maths. It was so important that they called the field, like arithmetic, geometry, probability down there. It was so important that they've sort of called it maths, okay, by calling it calculus. Okay. Now, what does it mean? Well, infinitesimal, that means really, really, really small, okay, effectively nothing, and we'll get to where that comes into a bit later. Okay. But just quickly, a bit of background. Calculus, infinitesimal calculus, was invented in the 1600s. It was so important and revolutionary that they effectively gave it the name mathematics, or what was used for mathematics in that time. And that's where we are now. So before we get into what is calculus, let's think of some of the other fields of mathematics. First, arithmetic. What is arithmetic? Well, that's the math of numbers and doing things with them, adding, subtracting, multiplying, basic arithmetic. Geometry, well, we've done a bunch of that over the years. That is the mathematics of shapes. Probability, what's that mathematics of? That's the mathematics of chance, okay, or uncertainty. Probability might be, what's the probability of me winning the lotto? What's the chance of Richmond winning the grand final this year? What's the uncertainty in pulling a red card out of a pack of cards? Okay, that's what probability deals with. Now, algebra, again, a little bit more difficult to define, but what is it? It is the mathematics of relationships. Okay, and more importantly in those relationships, and I'm just going to say between, okay, two or more things. Okay, so we generally have, when we think of algebra, we think of something like y equals ax plus b. We have some input we put in, which generates some form of output. Okay, and this rule or function gives us the relationship between the input and output. As we change our input, we get some given change in output. That's algebra. And importantly, it allows us to generalize. Okay, and I need to stop speaking slowly while I spell words, but it allows us to generalize. By that I mean, instead of just having one form of maths that we do, like take a temperature, do something to it and get a new output, it allows us to generalize and use it over and over and over again. An example being the formula to convert Celsius to Fahrenheit. That's generalizable. We can put in any type of Celsius, any degree in Celsius, and it'll give us the equivalent in Fahrenheit. It's not just a one-off, it allows repeat use and a bit of variability. So there's some fields of mathematics. That leads us to, what is infinitesimal calculus about? Okay, this is about all things that change. Okay, and the important word being change. Okay, what do I mean by that? Well, a simple example will be, let's talk about your position on the way to school. Your position changes, and the big thing about calculus has generally got to do with rates, and we'll get to this in a second, but the rate at which your position changes. Okay, so you might, when you first walk out the door, your velocity, which is change in position, might be low. Then you get in the car, it's going to be high. Then you get out of the car at the gate, you walk in, then you stop with your friends. Okay, so your velocity is constantly changing. And it turns out most things in the world change, they don't remain constant. Okay, so infinitesimal calculus gives us a way to approach these. How exactly? Well, it's through two different parts: differential calculus, okay, and the other one being integral calculus. And as you can see from the title up the very top, we are interested in differential calculus with this field on the left. What has that got to do with? Well, that's got to do with instantaneous rate of change. Okay, so in chapter 16, we looked at what we called instantaneous rates of change, and you can't see it at the moment, but I'm holding up my fingers to do little quotation marks when I'm saying the word instantaneous, because back in chapter 16, we said if time was equal to 0.01, or the change in time, triangle meaning change in time is 0.1, we could sort of call that was instantaneous rate of change. Okay, but it's not exactly. It's between 0 and 0.1 time frame. Okay, it's not exactly at just one instant. It's between, that's in that zone there. So we're going to look at finding rules or ways to calculate instantaneous rates of change, and that's really important, and it gets used extensively in physics and any sort of analysis, mathematical analysis, even finance, things like that. Now, integral calculus, and we will get to it eventually, but integral calculus has got to do with the accumulation of quantities. And what do I mean by that? Well, if we are talking over here in differential calculus, and these two are very related, okay, we go backwards and forwards between them all the time once we've learned both of them. If we're talking in differential calculus terms, we're talking about velocity, where velocity is change in position. We can use those velocities, we can accumulate them, okay, accumulate those quantities and find out our total change in position or our change in displacement, distance. Okay, so we can bounce between them, and then if we know information about how much accumulating of our position, well, then we can work backwards and jump into using that to find our velocity. So this is what infinitesimal calculus, it's a study of all things that change, and it gives us a mathematical way to describe them. Now, I mentioned previously, way back up here, okay, it was invented in the 1600s. It was invented simultaneously, okay, not together, but simultaneously by two different people. Okay. One of them you may not have heard of. Okay, he is Gottfried Leibniz. Okay, Gottfried. Now let me make sure I spell this correct. No, there, right. Leibniz. Okay, he was one. He was in Germany. He came up with it, and at the same time, someone else who you probably have heard of, also came up with this mathematics, and his name was Isaac Newton, or properly Sir Isaac Newton. Okay? But they came up with it at the same time. They weren't working together. They had communicated with each other and talked about it, and Newton actually had used a bunch of that communication to try and claim that Gottfried had stolen his ideas and that he plagiarized it, and Isaac was truly the real genius who came up with it, not Gottfried. But a review of all their communications and communications with other people, most people are quite happy to say that they came up with it separately, roughly the same time, and they're both equally responsible. Yeah. And there's quite a bit of history about the war between these two and how much it involved them. But so they came up with it in the 1600s. But why? What the hell were they doing? Well, let's start with something that we know and that they knew, and we'll then build into something that they were then trying to solve. So if we start with a linear relationship. Okay. They had a linear relationship, and I'm going to draw a quick one in here. Okay, we have a graph like this. That who knows what it is. It's some f of x, okay, where it's come from in the real world situation doesn't quite matter at the moment, but we have some linear relationship. Now we're talking about change. How much does something change? Well, we know, okay, change is a ratio of input versus output, or the control variable versus the independent variable. Dependent variable versus independent variable. Okay, it's a ratio of them, and we quite commonly know that as, okay, the change in rise, okay, versus the run. It's the ratio of the change in y and the change in x. Okay, and we have a quite lovely term for that. Okay, m equals rise over run, and we call this the gradient. Okay, the gradient of any function tells us how much it is changing. If I draw in another line, just over here, this graph, okay, for a given change in x or a given run, it has a quite large change in y. That means it has a high gradient. That means it is changing a lot. Now this other line, okay, not quite as much, but they knew this. We had maths to describe this, and the great thing about this, maybe great, but for us at the time, okay, doesn't matter how small, okay, if we looked between here and here, if we did the change in x and change in y for that section and compared it with the change in x, okay, and change in y in this, the gradient would be the same. That's the beautiful thing about a linear relationship. The change is constant. Okay? But we said these guys were dealing with all things that change and changing. Okay, and we'll get into exactly what that means. Linear relationship, big thing is gradient's the same the whole way through. It doesn't matter what sort of area we look at. They had the maths to deal with that. Now they were looking at something that didn't behave like that though, and especially Isaac Newton. Okay, what was Isaac Newton looking at? Well, he was dealing with this thing, and there's a very famous story about it, and I'll start to draw a picture, okay, and we'll see, okay, something like that. And then there was a little apple, and it fell down this way, and apparently it hit him in the head. And he thought from that, he came up with the concept of gravity, okay, or started to think mathematically about what gravity is. Okay, now whether the apple actually fell at all or something else, or it even hit him in the head, that's all up for debate. But either way, we do know though he started thinking about this idea of gravity. Now the problem with gravity, okay, is that it's not a linear relationship. Okay, it acted something like this. If we consider the x-axis distance and the y-axis the force it exerts, okay, gravity acts something like this. Okay, what does this mean? What does this mean? Well, one, it's not a straight line. It's not a nice straight line up and down, but we do know the greater the distance, the less force it exerted. Okay, and it wasn't on a constant amount though. As we got closer this way, the force it exerted grew rapidly. It grew very rapidly compared to the changes out here. Okay, it grew very rapidly, and we know now. Okay, we know now for gravity. okay, the force was directly proportional to the inverse, okay, of distance squared. So as distance increased, you squared that, and then force decreased by that equivalent amount. Okay. Now this is a non-linear relationship. Okay. You might think, okay, well, they figured out this, but that came from a whole bunch of maths that we're about to cover, okay, and proof and use and calculate. And thing was that Newton wasn't just thinking about an apple falling. He was looking at, well, if the Earth's gravity pulls apples down, well, the Earth's gravity means it's impacting on the moon. Why isn't the moon falling into the Earth like the apple is? Then that relates to, well, is the sun affecting the Earth this way? Does the sun affect all planets? And how does that affect orbital motion? Okay, so he wasn't just looking at apple, he was tracking and predicting the motion of planets. So not a very small task in the 1600s. Yeah. But the issue was, if we start drawing in something, if we look here, if we have a from here to here, okay, we can calculate the gradient between those 2 points, or we could come down here at a great distance. Maybe this is near the surface of the Earth over here. Maybe this is at the edge of the atmosphere, start of space, okay? And then maybe at the distance of the moon, okay? Might be something like that. And hopefully you're starting to see the issue already. And the issue was, okay, that the gradient was not constant. Okay, so m is not constant, okay, and importantly, we had no way, we couldn't calculate it. We could estimate it. We could estimate between here and then find a rough gradient for there, and here and find a rough gradient for there. Okay, we can make estimates, okay, but they couldn't actually calculate, and they couldn't come up with the formula for it. But they needed to, especially when they're dealing with planets and that. Well, they can't really make a little model of it and simulate it, especially 1600. They didn't have to calculate. You didn't have a computer or anything to run a simulation model, and to run a simulation model anyway, you need the maths. They didn't have the maths to calculate and make proper predictions. Okay. And they needed something. They needed something. Importantly, okay, is when we have gradients changing, and we'll go forward. So how did they approach this? Well, first off, okay, if we think of the problem back here, gradient, okay, first off, okay, we have a gradient there, a gradient there, a gradient there, okay. This gradient at the top would be a line like that. This gradient in the middle would be a line like that. This gradient down at the bottom would be a line like so. Okay, now these lines, these three lines, there's something very special about it. If we're trying to calculate the gradient at that exact point, because they're a straight line connected to a curve, they only cross it once, or they only touch it once, just once and only once, and these are called tangents. Okay, now tangents has a very another similar word in the English language coming from the same Latin root, and that is tangible. Tangible means to touch. These tangents just touch our function. Now the important thing about each one of these, if we just let's look at this one in isolation, okay, it only has 1 point. So since it only has 1 point, okay, how can we find the gradient? Okay, which needs 2 points. As per the rule that we know, m equals y2 minus y1 over x2 minus x1. Okay, we know that's the rule for gradient. Any gradient of any line, it's y2 minus y1 over x2 minus x1. The problem is this has 1 point. Now, some of you might think, okay, if we take this and if I have a really accurate line, I can put a dot here. Now that's great if we can graph this function. We have values that mean we can plot a whole bunch of blue points and we can get that. But when you're dealing with something like gravity, we don't have that data. Okay, it's 1600s. There's no spaceships going anywhere. All we have is the data for one very narrow piece on the surface of the Earth. We've got no data surrounding that. So if I then try and draw in a nice tangent line, well, I need to know the gradient at that point to draw that to get this second dot to then calculate the gradient. If you're listening carefully, you would hear me say, we need to know the gradient to draw this line accurately, to draw two dots to calculate the gradient. It's a loop. It doesn't work. We can't have the gradient to find the gradient. It doesn't work. But they came up with a way to do it. And that they went, okay, we're dealing with this line over here, okay, something like this, or any sort of curved line, it doesn't matter what it is, it could be quadratic, cubic, whatnot, dealing with those, and they went to, let's use something that we know lots about, that lots of mathematicians are working with, and it seems to be the turning point for a whole bunch of theories and discoveries, and that's circles. Circles everywhere in the history of mathematics. And they started by drawing these lines across a circle. One across, and what they did is they got closer and closer to the edge. Now quickly, so we have some terminology to talk about. This line that crosses, a straight line that crosses a circle, or even a function like this one, okay, if I draw a straight line across it, crosses twice, it is called a secant, okay? And then importantly, the distance between the 2 points it crosses, between here and here, the distance between those 2 points is called a chord. And generally, when we're talking about chords, we also label the points. So in this case, it might be PQ, the chord between P and Q. Okay. Now, what they did, like I was saying, is they moved the line this way. Okay, I'll draw it with where they moved it closer and closer to the edge. And look what happens to the chord. Chord there, chord there, chord there. Hopefully you're noticing the chord is getting smaller. And if I draw another one in there, okay, and then what happens right there is the chord disappears. There's not 2 points, it's just touching. It's one, okay? So what happens as they moved these secants further and further down, the chord length, okay, importantly the chord length changes, okay? So the secant becomes more and more like the tangent as the chord length approaches 0 in this case. Now we've looked at something that can help us with this. When we're dealing with things that approach values, okay, they might not be exactly 0 because we can't calculate. Like we said over here, back in this, we've got 1 point, we can't calculate the tangent, okay? But we can model something as the chord length approaches 0. We can model and make conclusions about something approaching a value using the mathematics of limits. We can do that. We've seen that before. We've worked with that. So it raises the question, how the hell do you get a gradient and a limit? Where's the limit in this whole idea of a function? Okay? Where can we get this from a function? So let's take a basic function, f of x, our blue line, okay, and we're going to draw this red secant across it. Now wherever we draw, it doesn't matter where the hell we draw that secant, okay, we get 2 points. Now the first point, this is what Newton and Leibniz did, they'll say it is at x. Cool, easy enough. And then they said, okay, that the next point across, this point here, will be some distance further, okay? Some distance further, okay? Some distance further this way, okay? And they said that some distance is h. So this point here, we have our original point x, this some distance further along is h distance greater, so it's x plus h is the coordinate. Now, okay, all well and good. What comes from this? Well, if we put these values, okay, put these values into our function, okay, we get our output, we get our y value. So let's look at the first one. If we put x into our function, we get a result, a y value of f of x. Easy enough. And then our second one, I'm going to start color coding this, our second point, x plus h. If I put that into my function, I'll get some y value, okay, that is a function of x plus h. So what do we have here? We have 2 points. We've seen this before. We have 2 points, and we can find the change, the average rate of change, or the gradient of this red line going through these points using, quite simply, rise over run. We have 2 points. We can do that. So let's substitute those in. And quickly, as a refresher, if you're forgetting, rise over run is the same as y2 minus y1 on x2 minus x1. Okay, and the green dot is our second coordinate point, and the blue dot is our first coordinate point. So let's use some colors to color code this. So y2 is our y value, so that's going to be f of x plus h. And then it's going to be take away our y1 value, which will just be f of x. And that's all going to be over x2. Our x2 value is x plus h. Okay, that's our x value right there. And then we'll take away our x1 value, which is just x. Now there's one simple simplification we can do. We have an x plus h subtract x, so x cancels with the x, and we are left with this function that says f of x plus h minus f of x all on h. This is the gradient of the secant. It's the rise over run between these 2 points. It is m secant, f of x plus h minus fx on h. This gives the gradient of any secant. Okay, it doesn't matter where we put it on the function, it gives the gradient of the secant. But we don't care about the secant. Okay, we've done that. We've done that here. We don't care about between 2 points. We want to know an individual point, here or here or here. Okay, what we've looked at with this stuff. Okay, so how do we turn this from the gradient of secant into the gradient of tangent? Okay, think of back here, we move the line closer and closer to the edge. What are we going to do with this? What can we do this? Okay, similar sort of idea. Where are we going to get a limit from this? Okay, what we're going to do, and it all relies around this. Okay, some distance further. We make h smaller and smaller until it approaches 0. We make h smaller and smaller. So this line, okay, if we went to halfway here, we made h, well, it would be between there and there. And then if we changed it to here instead, that's x plus h, we get between there and there. And we get to this point where all of a sudden h equals 0. Okay, or we make it smaller and smaller. How do we do that? How do we make something approach? Okay, as we said over here, it's using limits. So to change the gradient from a secant, we just make h smaller and smaller until it approaches 0. We take the limit of this, as h approaches 0. So we get limit h approaches 0 of our secant function, which is just f of x plus h minus f of x all on h. Okay. We make h smaller and smaller till it approaches 0, or we take the limit. That's what this sentence right here means, is pretty much take the limit. So we get this function, and this was the brilliance of what Newton and Leibniz did. We've now got a function, a rule that tells us the gradient of the tangent, not the secant. We now have a rule for the gradient of the tangent. Somehow we've got the gradient of the tangent with only 1 point, and it's absolutely brilliant. So we now have what's called, as a great person said, the science of fluxions. Now that's what Newton wanted to call this, the science of fluxions. Now I reckon that's pretty cool, pretty out there, a bit, I don't know, so spacey, quite out there, but luckily, I guess in the long run, it was changed to just being called calculus. That's what Leibniz called it, or infinitesimal calculus, and that's what stuck. Okay, so using the equation that we made on the last page, this equation down here, this is everything. This is the whole point of this topic. Okay, this is the money. Okay, that's the win. Okay, winner, winner, chicken dinner. Using that function, we end up getting a new equation. Okay, once we substitute some values into the function on the last page, we get a new equation. This new equation is called the derivative. Okay, and it tells us the gradient, okay, for any point we choose. Doesn't matter where on the graph. We could choose the very start, the very end, anywhere in the middle. It will, using this function we get at the end called the derivative, will tell us the gradient at any point. The process of creating this function, so the process of using this, okay, when you substitute values in, the process of creating the derivative, okay, is called differentiation. Okay, you differentiate, or you do differentiation to get the derivative. Okay, and this is where this differential calculus comes from. It's a play on derivative and differentiation. Now with this, we're doing some maths. We've got this thing called the derivative, and it tells us a gradient. We need some notation. So we started with some rule, f of x, okay, and we want to know the gradient of it. Okay? So we use this notation here, f dash of x. F of x is our original, okay, original. F dash of x is our gradient function. Okay, it tells us the gradient at any point, which is called the derivative. Okay. Now that's if our original thing is called f of x. Sometimes our original function is called y equals blah 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 blah. Now if it's y equals instead of f of x, we use this notation for derivative. This also means derivative. Okay. Now, dy dx, that's how you say this, dy dx. Where does dy dx come from? Okay, well, we know some other, it means change in y over change in x. That's what gradient is, okay? And we have some other symbols for that. We know delta, this triangle symbol, is Greek delta, okay? We know that means change, okay? And then we have, that's a capital delta, by the way, and then we have lowercase delta. Now, lowercase delta, I can never write these properly. I'm going to give it a crack, but oh, and that's a terrible one, okay? Well, that's a lowercase delta. Okay, that means small change. Now, we're not just dealing with small change, are we? It is small change, but we're dealing with the limit as h approaches 0. We're dealing with infinitesimally small change, super tiny micro, effectively zero change. So what symbol are we going to use for that? We're just going to use d. Okay, infinitesimal change. Okay, effectively 0. But that's what this is. Dy dx means change in y over change in x. That is really small. Okay, equals, and this is our derivative. Now, I know there's lots going on this slide, and I apologize for that, but I think this is really important, okay, to understand what the words actually mean rather than just doing, oh, when I see a question that says do this, I'm just going to use this equation here. Okay, it's better to understand where this comes from. Okay, so a bit of background in sciences, and mathematics was a science, is a science, is the word's first principles means something is a self-evident proposition. Okay, self-evident, or an assumption that cannot be formed from any other principles. Okay, a self-evident proposition or assumption that cannot be formed from any other principles. Now, when Newton and Leibniz came up with this mathematics, there was no, and I've got here remembered because there was some stuff sort of figured out a long time ago, but had been forgotten or lost. There was no remembered or established mathematics surrounding continuous change. Hence, the above equation is called the first principle of differentiation. So this equation right here, okay, what we said, the money, okay, is called the first principle of differentiation because you can come up with this idea like we just did here, working down this process using self-evident propositions that aren't formed from other principles. Okay, it is a standalone idea that is just self-evident. Once you see it, you go, yep, that makes sense. That's what it, that just makes sense. I don't need proofs or anything like that. It is self-evident. Okay, and because of that, this equation is called the first principle of differentiation. Now, there's a whole bunch of other ways we can do differentiation. Okay, the process of coming up with the derivative. There's a bunch of rules and shortcuts and a whole bunch of things, but this one is called the first principles method. Okay, and let's do an example. Let's tie this all together with the final example. So we have a function here. This looks very familiar. It's a parabola. I hope it looked familiar to you. Okay, and it's f of x equals x squared. So like I said, or it's y of equals x squared. Now, like I said on the previous slide, we've got to be careful with notation, okay? And for this one, we'll get rid of that and we'll just pretend it is f of x equals x squared. Okay, so that's our original function. We want to find the derivative, okay? This f dash of x, that means derivative, okay? A function that gives us the gradient at any point. So we'll apply first principles using this equation here as first principles, but we'll start from the very start. Let's pick a point on the graph, call that x, okay? And that means we get an output, okay? If I put x into here, okay, I get out, shock horror, x squared. So my output right here is x squared. Now if I pick some point some distance further along, remember that thing, some distance further along, okay, h along, that means this coordinate here is x plus h, okay, and I will get some output. Now that means I get, if I put x plus h in, okay, into my function, my output will be, well, x plus h all squared. I'm putting that into the function. Now if I expand that, that gives me x squared plus 2xh plus h squared. So I get an output of x squared plus 2xh plus h squared. That is my output for my second point. So let's use that now. That at the moment is a secant. How do we turn it into a tangent? Well, we take the limit as this some distance further h approaches 0. So we can substitute these things here that we found into our function, into our first principles function, and I still have to write limit. I always have to write the word limit as h approaches 0 until I actually solve the limit. Until I solve the limit, I need to put this in. And that's really particular, and I'll smash you marking wise if you don't do that, because you've put an equal sign, so it means it needs to be equivalent to the line above. If you don't put this notation in, it is no longer equivalent. So we substitute this in. F of x plus h, we said, is that, so we get, and I'm going to put in brackets to avoid any sign errors, okay, minus f of x, which is x squared all over h. Okay. Now I can't solve that limit yet. I can't solve that limit. If I put h equals 0 into here, I get a denominator that's 0, divide by 0, breaks the universe, everything ends. No, not really, it just, we get an undefined function. So I need to do something. And if we, let's see what we can do. Okay. First off, we have x squared plus 2xh plus h squared minus x squared. There's some cancelling we can do. X squared, take away x squared. We cancel those out, and we are left with 2xh plus h squared on h. Now we have the same issue. We still can't, okay, solve this limit because we have a denominator that would be 0. So what do we do in these situations? We factorize. We've talked about this before. H towards 0, okay, and I'm going to take out the common factor of h. Whatever the denominator is, I'm going to try and take that as a common factor on top so I can cancel. So I get 2x plus h all over h. Okay, now lovely, we get that. Okay. And now I'm left with, and I'm going to show the full working out just so everyone can see it, 2x plus h. The f dash of x, remember this is what we're dealing with, is equal to the limit as h approaches 0 of 2x plus h. I can solve this limit. I can, in here, I can let h equal 0. That's how I can try and solve this limit. And I'm left with 2x. I'm left with 2x. What is this? What is this? It goes to this. It is f dash of x. It is the derivative. It tells us the gradient at any point. Okay, any point on for this original function tells us the gradient of any point. So let's use it. Since we found this rule, let's use it. Let's go 1, okay, gradient at x equals 4, and we'll do second problem of gradient at x equals -2. Now, gradient x equals 4. Well, f dash of x tells me the gradient. Okay, now it's going to be equal to f dash at 4, which is equal to 2 times 4, which is equal to 8. So the gradient, okay, at x equals 4 is 8, and I guarantee you that is true. Now if I want to find the gradient at x equals 2, I need f dash of negative 2. F dash means the gradient, or the derivative function, equals 2 by negative 2 is equal to negative 4. The gradient at x equals negative 2 is negative 4. Okay. Now this is a pretty simple case with a simple function, f of x equals x squared. But it's a curving function. I've now given you a rule, this thing right here, that'll tell you the gradient at any point. Doesn't matter, you could say x equals 1,000,000 and this will tell you the gradient, okay, which would happen to be 2,000,000, 2 times the x value. How did we get there? Well, we started with our first principles equation. Okay. First principles. Okay. We substituted. Okay. Some cancelling. Okay, to get to here. Okay. And then we factorized. And by factorizing and cancelling, we now had a limit that we could solve. And we solved the limit and we got our answer. So, long video, thank you very much if you stuck all the way through that, but that is an introduction to differential calculus. Introduction of the history of it, very briefly, okay, what it is, and a look at the first principles. I apologize now that I've had to stop for a second and look in the slide how messy that is. Okay, hopefully you didn't copy all of that if you're copying along. Okay, but you have some idea of what this process is. We differentiated using the concept of first principles to find the derivative function, which was this, and then we used the derivative function to find the gradient at certain points. Now again, like I said, f of x equals x squared is easy, but this can work for like x cubed plus 3x squared plus 4x minus 5. Now if you graph that function will be a wee, something like that, but we can get a derivative that tells us the gradient at any point on that. So that is really handy in the real world for physical applications, financial applications, or anything to do with something where it's changing, which is pretty much everything. Thank you very much. If you have questions, stick them on the Edmodo page or in class on Monday. Thank you and bye.